Okay, first of all, let me thank the organizers. It's a wonderful place to be with wonderful people. So I will present today in a hybrid format joint work with Matthias Stout. And it's a hybrid format because he also has a poster with some other approach to the same subject. And you can look at the poster and ask him extra questions whenever you want. I will start with a motivating question that was raised to me a couple of years ago by Rami Eisenbud. And it's about the Fourier transform of some p-adic functions. Suppose I have a finite field extension of QP, and I have another finite field extension, L of K of QP, and suppose I have a function fk on k to the n, and say fk could be given as the p-adic norm of a definable function. In that case, I can also say I look at the same definable function on the field fl and take it as a function on L to the n. And as I say, it could be the norm of a definable function, so it's real valued. So I can consider the Fourier transform in both cases of fk and the Fourier transform of fl. What can we say? How can we compare Fourier transform of one with Fourier transform of the other if they are given in a nice way? And a natural question that comes to mind is the following. Suppose that I know something about this one, and in a large field, the philosophy is that you see more than in a small field, like in geometry. That's somehow a philosophy. Suppose I know this Fourier transform is a locally or globally L1 function, or more generally, some LQ function for some value Q. Can I induce from it, or under which conditions on fk and fl and the formula defining the graph and so on, that also this function is L1 or LQ or locally L1 or whatever you want to induce from a large field to a small field. So there are a lot of things that can go wrong here because definability allows you to express so many things, so many more things than just say equations of polynomials. But a first conjecture and a first guess could be the following conditions: that maybe fk is the graph of a function, is the norm of the graph of a function which is given in a quantifier-free way, in a simple language, in a basic language like the language of valued fields, or the language with an RV structure extra on top of it, quantifier-free. And then also maybe if you want to consider functions which are more general than just the norm of a definable function, you could still ask it to be the fk's to be non-negative, because if you allow positive and negative parts in a build-up of a function, seeing more may also kill more because of the plus and minus signs. But still, this question is widely open, if that's enough, because this is not even a piecewise question. If you restrict fk to a definable subset of k to the n, the restriction may no longer be L1, where the complete function is is L1. And that's because Fourier transform is sensitive to curvature. So if you restrict to a thick curve, the neighborhood of a curve, it may kill being L1. So the only case where this is not too hard to verify is when n equal 1. Then you can control the behavior of this question. So this is still very, very much open. And to make it precise, the question is, how nice should this collection of functions be? How nice should they be? A second motivating question is starts with a polynomial, which I also denote by f, over the integers in n variables. And I look at finite sums. In Fourier transform, it is described by an integral which involves oscillation. Here it will be a finite sum involving, again, some oscillation. And I denote it by exponential sum, the e, of a parameter p to the m. And I put an index f, and maybe also the QP for the base field. I define it on the base field, and then I let it to your imagination to define it on K and L. And actually it will be the complex modulus of a finite exponential sum, where I sum each of the coordinates in z modulo Pm, Pmz. I take the complex exponential of 2 pi I, so I'm on the unit circle, and here I plug in a rational number, which is f of x, which is determined only modulo p to the m. So if I divide by p to the m, the rational number is sufficiently determined to give this a specific complex value. And I normalize by the number of summands. So that by a trivial way, this is always at most 1. Now, what one can do is observe that this quantity very often, or always actually, will allow some sigma for which it goes with a certain decay for some sigma. So there are rational numbers or real numbers sigma such that it goes to 0. And sigma can actually also be 0. It can go from 0 to plus infinity. And the optimal value for sigma, so this can also be redescribed as a p-adic integral. It's known how they can qualitatively look, these integrals. And one knows that the optimal sigma, which is the supremum of all the possible values that have this equality for each epsilon, the optimal sigma makes this also hold. And for the optimal sigma, you can denote it as sigma over qp of this exponential sum. And then you can have the same finite field extensions L and K over qp. And you can wonder whether you have a kind of semi-continuity for the optimal sigma. So you can look at the value over L of this E, and you can look at the value over K for the analogous definition of the optimal exponent. And here, if you see more singularities over L, then the upper bound should become worse, and this translates into this inequality. So this is also a question whether if you see more of the singularities, more singular behavior, whether the exponent automatically becomes worse or stays the same. This is a very open question. What is known is that if you look at all the p-adic fields, you get a bunch of optimal exponents, but in fact they all live in a finite candidate set. So you only have finitely many values that can occur among all the all the optimal exponents. Let me now give a motivating situation where we can actually show a similar kind of semi-continuity of the optimal exponents. And this semi-continuity, you can also see it as a property of descent. You go from a large field, a large p-adic field, to a smaller p-adic field, and the invariant that you study can only move in one direction. So you go down to a smaller field, so it's a descent property. Instead of this oscillatory behavior, let's now just look at finite counting as done by Denef and Iguza, and was questioned by Borovic, Safarevic. But let's look at the variant of the question by Borovic and Safarovic, raised by Serre. And that was studied first by the Neff. So it's the Serre variant that I will introduce. And by the way, maybe you can call it also Serre de Neff variant. I think because the Neff was the one who addressed the question on it by Serre. And I take the same polynomial here, f over the integers, and I look at a number now, the Serre variant of the counting with index m, or you can also put the p-adic numbers as an index if you want. And it's the normalized count, so I divide by the number of summons, and I count, and I open my set, and x runs in the same index set as there, z modulo pm, in all the coordinates, such that, and now I just ask something slightly more complicated than in the classical situation. I ask that there exists an exact p-adic solution. So this is something with a quantifier of f, so fy vanishes exactly in the p-adic sense. And at the same time I ask x to be congruent with y, with the exact solution modulo p to the m. So in the beginning I made a conjecture or a guess, a simple first guess, that your data should be given in a quantifier-free way, but actually here I'm in a simple quantifier. It's a quantifier, but it's a simple quantifier in some way that I will describe later. So quantifier-free or simple, nice, easy quantifiers will be good, and I will make this precise in a minute. So for these counting numbers, you can have the same kind of upper bound of this form, some constant depending only on epsilon. You look for which real value sigma you have this upper bound for all m, and then you look at the infimum of these values in sigma. That will give the optimal that will give the optimal sigma, and the supremum of the sigma for which it holds gives the optimal one. And then you can ask the same question about, so for the Serre variant on L, actually it will be a result that follows from the main theorem I will state in a minute, that the Serre variant for K, for this polynomial f, you can put indices to make things explicit if you want, to have this kind of descent and semi-continuity property. So what can you observe here? It's that this formula is an existential formula. It has existential quantifiers in front, and then follows just a quantifier-free formula. And of course, existential formulas are known to be nice when you go from a substructure to a larger structure. They can only see more, and they cannot see less. They cannot suddenly not see something anymore. So this is a behavior that that we want to capture with the descent property.
Can we ask a question?
Sure.
Is the f on this middle board related to the f on the board on the left board?
No, that's a different. This is just an abstract function that I didn't specify, that is given in some uniform field-independent way.
That one is complex value or real value.
This is a real valued function. F could be, for example, as an example, it could be the k norm of that polynomial, of a polynomial. Or maybe restricted to Zp to the n and put 0 outside of Zp to the n. Could be like that. Or 1 over that, or something like that. Yeah. Is that?
Can you say what the definition of a Fourier transform is?
Yes, it's like in the real case, you take an additive character on Qp, and then all the other additive characters are a composition of a homotopy with that given chosen one.
Additive characters on Qp correspond to, or do they, is Qp like self-evolving duality, or is it
To the complex unit circle, an additive character is a.
I mean, is
Yes? Yes, and it's isomorphic to QP again. So the Fourier transform of a function on Kn is a new function on Kn after identification. It's again a function on Kn. So you can see many properties about it. So on this new, for this new function on Kn, you ask is it L1 or locally L1. Yeah.
In the second picture over here, you are letting n go to infinity, and does that converge to the Fourier transform on ZP or something?
It's a good question. So this one relates to the Fourier transform of another function, the Hennenfent singular series. Its Fourier transform evaluated in certain points is exactly this value. Yeah. So yes, it relates to a certain Fourier transform of another function by Fubini, by some Fubini argument. So I want to give you some more examples about seeing singularities or not seeing singularities. And for that, it's most handy to introduce the classical counting problem, which goes back to a question raised by Borovich and Safarovich in their book on number theory, which was addressed by Iguza using embedded resolutions, now also called log resolutions. And it's the same setting here, but you don't consider the y's. So you count in the classical situation for m and qp, and let's put the index f for the polynomial also. It's the normalized counting of the same objects, but now you just want f of x to vanish modulo p to the m. And Iguza showed that the generating power series of this one for all m, if you with m t to the m, you can make a generating power series. It's rational, it has a meromorphic expansion, but this is not the question that we want to look at here. We want to see again the optimal exponent for the upper bounds, and then you see that the sigma classical one of L again here is at most the 1 over k. But the upshot of this example is that it's easy to compute examples. If you give yourself a simple polynomial, you can do an explicit computation because this is a simple thing. And let's start with very basic examples. If f of x is the zero polynomial, that's the most easy example. You all know that doing examples on a blackboard is dangerous. So let me keep, then this optimal thing, the classical one, for any k is actually also 0. You cannot have any good upper bound. You only have the trivial upper bound. Another simple example is when it's smooth, and the most smooth thing is just a linear thing in one variable. Then this is 1. And a third trivial example is when it is non-vanishing. If it's like a unit, then every bound holds, so the optimal one or the limit value for all the bounds is plus infinity. But in most cases it's not plus infinity, and if it's not plus infinity, it will be between 1 and 0. And me give you two more examples. If it's x1 square.
So what I'm confused, what is this superscript? What is written everywhere? Sigma L something.
Classical.
Oh, I see.
This is the classical counting. If it's x1 square, you get a half. So it's the multiplicity in this case. And if it's a sum of things like that, x1 to the d plus x2 to the d prime, where d and d prime are both at least 2, say, then it's 1 over d plus 1 over d prime. So you get a certain kind of additivity of multiplicities if the terms are in separate coordinates and so on. So you can do explicit computations, and this helps you to see that sometimes this inequality can be strict. Let me give an example to see that. If your polynomial is like x1 plus 1 and then x1 square plus 1. So in some p-adic fields this will vanish. In other p-adic fields this will never vanish and will be a unit, and then it doesn't matter so much in the counting process. And if you multiply this with x2 x2 for example, then you can get two values for the optimal exponent, and it is really the phenomenon is if you see more, the value becomes less. So if you only see x2, it's like the linear example, and you get 1 as the optimal exponent. But if this vanishes, you immediately have something of multiplicity 2, and you get 1 over 2, and then this is somehow not relevant anymore. So in larger fields, you can get a smaller sigma. In small fields, you can get a larger sigma. Let me also give you a polynomial where we have some problematic behavior that we don't want. So it's some behavior that we want to exclude. I take a kind of a piecewise polynomial. And it's x1 square plus, and now a case distinction according to pieces, x2 square. So we know how to do that kind of polynomial by x1 to the d plus x2 to the d here. But I only take this polynomial if there exists a z with z square equals minus 1. And else, I take 0 value. So this is in every field this becomes a polynomial, but it may be a different polynomial depending on which field you interpret this function in. So in every field you can define the classical counting for that polynomial, but you get the wrong inequality. Because in a large field, sigma L is large, you see the root of minus 1, and then you get 1 over 2 plus 1 over 2, so sigma L could be 1, but maybe in a small field, you have the value 0 here, so you just see x1 square, and then you have sigma small field could be 1/2, which is the wrong way it jumps. So what is wrong with this thing? Well, in a way, if you look at the integral behind this counting procedure, you will see that this is also described or governed by an integral, but not by something which is given by an existential formula. Because the complement here, this complementary description, requires universal quantifier or something, so it's not nice enough. That's a problematic example. Let me now give the result that we can do, and from that result follows the descent.
Is there some qualitative connection between these sigmas, and if one is 0, then the others are 0?
Yeah, sometimes maybe, Yeah, being a polynomial to be 0, identically 0, that cannot change when you change your field. So sometimes, yes. But in general, you can see more of the polynomial if you go to a larger field, of course. Yeah. So let me state you a theorem. I consider now a function from xk, which is a subset of k to the n, and it's k valued. And the graph of the function is given by an existential formula and if you specify the shape of your sentences, it's also important to specify your exact language. So let's use the language with RV structure. And by the RV structure, I mean that you have not only the sort RV, which is k modulo 1 plus m, with the RV map from k to there, but also for modulo some integers. So if you have an integer n bigger than 0, I also consider the sort RVn, which is k modulo 1 plus n times the maximal ideal, not the exponent, but n times. So it could be p times the maximal ideal, or to see some part, so a large part over big residue rings and so on. So then I call this RVn. So I call this whole language LRV. By an existential formula, as I said, I mean something in the beginning. There are many existential quantifiers, bracket open, and then a quantifier-free formula, bracket closed. And then what can we do? We can look at the integral of over xk. So this function makes sense since its graph is given. Let's say it makes sense in all the p-adic fields that you want to consider. It gives a graph, let's say, in all the p-adic fields. You can integrate them over xk, the norm of fk, and we want to, like in the beginning, we want to study, is it integrable? Is it L1? Is it L2? Is it LQ for a certain value q? But we do this cleverly by putting a complex power. If you put a complex power number s, then you can see, well, the real values are sufficient, of course. You can see if you put 1, you study L1 integrability, if the integral is finite, and so on. So, but now it's a function depending on a parameter called a local zeta function, z of s over the field k of the function f. You can again put all the information as indices if you want. And suppose for convenience that it's L1 when the real value of s is very large, or even so in the limit for very large s, suppose it's L1, then you can look at where does it stop to be L1. That's a kind of a limit value for the function fk to be LQ or L integrable. So this is the infimum of all the values where it is integrable. And this again gives the value sigma. You could call it the value sigma. You can do that in the field k for the function f. Let me write it like that. And you can also do that for L. But now seeing more, there is somehow a sign change. So seeing more singularities now becomes that it stops more rapidly to be integrable. So if it's integrable over L for a certain s, then it's also integrable over k for a certain s, but maybe in k you see a bit less, so you can go beyond. So this is a sign switch. Sorry about that. You can also take a sign switch and then have the same inequality as before, of course. You can also see that this local zeta function is actually a rational function. It's a rational function. It's known to be a rational function in q to the power minus s, qk, where qk is the number of residue field elements. And then you can look at the poles of this thing, the real values of the poles, and then the largest real value of all the poles is also related to where it is integrable or not, to this limit value. So in a way you also get descent for exactly the limit value of all the real values of the poles.
The K is always ramified?
No, it's any finite field extension of QP, and L is any finite field extension of K, so it could be highly ramified. And P can be small. P can be anything also. It can be 2 or 3, or any prime. As a corollary of this theorem, before I give the ingredients of the proof, we get the previous two examples for the Serre variant and for the classical variant of the Poincare series that was studied by Guza and Denef.
So the L alpha information on this side will transform into a sigma information after you take the
No, now I'm not taking Fourier transform anymore. This was just a motivating question. Now I'm just looking at the norm, the k-norm of a function in x. I'm integrating over x, so no oscillation anymore.
The sigma is the number or to the right it's integrated?
Yes.
Does the exponent has to change L1 to L?
Say it again?
Is the point of the exponent has to change the L1 to, like, change L2 to L1 or that kind of thing?
You have to take compatible norms. That's no, it does not change L1 or L2, but if you go from the real to the complex and you compare real integrals with complex integrals, you get a factor, an exponent, multiple 2 in the exponent, and for some calculations and so on, but this does not happen here because the Q already, you have a different way of capturing these, because you take a Haar measure that adapts itself also, and the change in exponent is hidden in the change of Haar measure that you take on K, and on L you take the Haar measure. You can play the same trick on R and C, and then the 2 would not. Is that where you are thinking about, or? So let me address your question maybe at another level. So here you can say if FL is LQ, then also FK is LQ for any chosen value Q. Not Q, yeah. LS0. LS0.
So the S there has to do with LF, right?
Yeah. Yeah. L is a finite field extension of K, so you can interpret the same function. F is a definable function. You can look at it in a p-adic field. Here it's the Lebesgue. This is Lebesgue L. So Lebesgue L, meaning integrable. The power is integrable, a finite integral.
Function in between the optimal exponent precise selection is right.
Yeah.
You just write one in terms of
Yeah. Let me tell you, before I go into the proof details, let me tell you about some caveats. So why do we take the language with RV, and why don't we take the language with Denef, which is called Denef-Pas language with angular component maps? Because that allows you more easily to write an integral as a sum over the value group and a sum over the residue field. While here, we will rewrite it as a sum over subsets of RV, which are a little bit less visible what they do. Well, there is a specific reason for it, because the existential formulas, they behave well under substructures. If you have a substructure of something, and here the LRV language is so natural that any finite field extension can be seen as a substructure of the bigger field. But with angular components maps, this is problematic. If you have an angular component map on K, then maybe you cannot extend this same angular component map to an angular component map on a larger field. So it is not a substructure. And even worse, there can be certain finite field extensions so that no angular component extends to an angular component there. So you cannot see it at all as any kind of substructure in the Nef-Pas language. So we had to stick to this more natural language, more intrinsic language. Another thing that I want to stress is that in the beginning I said in my basic conjecture, that there should be some non-negativity, some positivity into play. That can help. Where is the positivity here? Well, this function, the norm is real valued, it's non-negatively real valued. That's the way. And if you want, you could also consider a slightly more general situation where you have a sum of such things, F, L, K, K, and then do the whole bunch to the power S. So then you really see it's a positivity notion that you can take sums, but you are not allowed to take differences because then you can mess up behavior. Okay. The proof, or the idea of the proof, the strategy started with the idea that existential quantifiers in the LRV language, they can be controlled by eliminating them and only keeping existential quantifiers over RV, over the auxiliary sorts. So, of course, one knows that there is a classical relative quantifier elimination result. You can eliminate valued field quantifiers quite often at the cost of ending up with quantifiers and difficult expressions over the residue field or in the value group and RV. But here we can do this in an existential way. So let me write it out. Any existential formula in LRV is equivalent to an existential formula in LRV with only quantifiers over RV only. So RV, I mean all the RVN only. Equivalent for what theory? Well, the theory of characteristic zero Henselian valued fields. So the value group can be general at this point. The residue field, the ramification can be general because we have RVN to deal with, to hide the difficulties from ramification. So the theory of Henselian characteristic zero, just it could be mixed characteristic zero valued fields. But that's not enough in general to know quantifier simplification is not handy enough to understand integrals. You also want to prepare definable functions to simplify them in some coordinates, integrate some coordinates out, and at the end you want to have a sum over the auxiliary sorts only. Here in this case the sum over RV. So there is a proof scheme for cell decomposition for that we reuse, and it was first developed by Cohen and then put in a more model theoretic context by the Nef and put in relation with integrals by the Nef, and Pas made it uniform, and that proof scheme can be redone to have a cell decomposition which is existential. So any definable set xk, like in the thing, can be decomposed into what we call existential cells. And I will give later an idea what it is to be a cell and also on which the function is prepared. So we had this function fk is prepared, and that means that the RV of the function is actually quite simple on the cell. I will give a specification of that a bit later. But this, this tool allows one to integrate one of the variables out, or integrate one by one with respect to, of the variables, and replace the integral over a k variable by a sum over RV variables. So we end up, we end up with a sum of a certain kind of subsets with some variables xi in D and a fiber over some zeta, and then some value q to the power order of zeta 1 and order q to the power order of zeta 2 times s. So we have some q powers, we have some q to the s powers, and then this is always, for each fixed zeta 1, zeta 2, this is a finite subset of RV. So we rewrite it in a way so that this is finite sum. And then we can see, well, if it's empty over k or non-empty over k, that plays a role, but it can only change in one direction when you go to a larger field. Non-emptiness can only be preserved when you go from k to L, and something empty can become non-empty when you go to L. And this finite sum, we see it doesn't matter so much in controlling the summability, the radius of convergence and so on, if you then also sum over zeta 1 and zeta 2. So in a way, this replaces it to just looking at which zeta 1 and zeta 2 does such a sum appear and is not zero, and you control then the integrability by just rewriting it as a sum over RV. Here we use a little bit an angular component to estimate these finite sets, but this is just a local trick for estimating it for a specific field k. What is the upshot of having this kind of semi-continuity or this kind of descent, like here? Sigma s for a large field can only be in one way ordered to sigma of k for a smaller field. That is that you can look at the limit value for larger and larger field extensions. It can only go in one way, and you know that there are only finitely many candidates values for it. So you can look at the limit value, and that will be a value that makes sense for all the fields because you know how it relates to all the other values. And this gives a lot of new invariance, where in the reals you can go to the complex numbers, but then it stops. You only have one option and it's immediately done. Where for each p you get a potentially different limit value.
Can you get the best n?
Yes, after it's realized after finitely many large.
So you can identify it.
No, not in general.
Is it a finite extension or not?
Yeah. So now I have to erase a little bit. So now I will give some small compliments, like some extra open questions and some extra delicate situations. Let me tell you the example where you cannot extend the angular component map from K to L. And that's given by an Eisenstein equation. If L over QP is a finite field extension which, as a minimal polynomial, has a certain Eisenstein equation plus px plus p. If that's the minimal polynomial, I will just indicate it. Then, in fact, if you would have a system of angular components, so not only the first digit, but also where you see digits modulo n times the maximal ideal, so you see many digits, then you can argue certain reasoning on the discriminant that in fact it should come from the equation xp to the n minus p equals 0. So it gets into, so if you would be able to lift all angular components here, two angular components here, you can deduce by reasoning on the discriminant and on uniformizers, because a system of angular components is uniquely determined by a choice of a uniformizer. And the same here. You can reason on that to force L to be actually come from something of this form, but it doesn't, because it comes from that form, which is different, as you can see by looking at the discriminants. Okay, that's just to be a bit more explicit. Let me now at the same time raise another open question and give you some more intuition what this cell decomposition do for preparing the RV of a definable function. And I will give that intuition by going to Hensel minimality. So now I take any language which is potentially much bigger than RV language. And here in this language, not every field extension will automatically be a substructure, but you can look at substructures in that language. So you can look at finite field extensions and suppose that they are L substructures of each other. And you can require L to be, or you can require these structures to be Hensel minimal. And then I will explain what this means, but the question I want to do is not only explain what that means, but also can you do descent under some extra conditions in Hensel minimal structures with some existential condition built in. But the Hensel minimal, the structure on K is called Hensel minimal. The definition is long and technical, but the idea is very simple. It's just about unary definable subsets of your field. For such a definable subset, there should exist, in order to be essentially Hensel minimal, there should exist a definable finite set. And definable here means with the same parameters as over which X is defined. And what does C do? This finite set C prepares in a way the set X, and it can simultaneously prepare a definable function on X. And what does that all mean? If for X in K, the condition whether X belongs to xk or not depends only on the values, the RV values, or the RVn values for some finite n, you could say, of X minus C, where C runs in this finite set. And if you you can do the same for O minimal structure, where you use the sign condition for the boundary points of the intervals and the isolated points. The sign condition determines whether you're inside or outside an interval. And if at the same time, so that's the definition essentially of Hensel minimality. But if you are Hansen minimal, you can prepare at the same time a definable function. If that's given on x, the RV of f of x also only depends on this tuple, these RV values of x minus c. So it linearizes, it makes a difficult, potentially difficult definable function just depend on linear values, linear things from the valued field, and then some values in RV. So it linearizes your problem. So this is one open question. The other open question I want to repeat is what for Fourier transforms or the exponential sums. And then in the last few minutes I want to go to another question of semi-continuity with a slightly different flavor. So give me a minute to erase. Are there questions, by the way?
I have one.
Yes?
So there was an implicit assumption in your, I mean, the same extension formula might not define a function for large or field extension. Do you assume it does for every finite extension, or do you then adapt the
Yeah, we start.
But then there is another quantifier entering the picture.
Okay, yeah, we start actually with a uniformly given definable function, which happens to be given by an existential formula.
So it's even in every finite extension, so it's functional.
Yeah, because indeed, not any formula which is a function in some fields is maybe not a function anymore in other fields.
So you cannot do it for every finite extension where it is a function, blah, blah, blah.
Yeah, that's also possible probably, because that's a definable, I don't know if that's existentially definable condition. You would have to check in your example if that would fit. It's not existential, yeah. And yeah, good variant question. I'm not sure, but in fact, it's most natural to look at substructures, just K and L. You look at two structures where it is a function, and then you want to compare. Yeah, good question. If that's, I think it should work because you just need substructure of another and an existential formula. Yeah. Okay, finally, another semi-continuity question. It's about these finite exponential sums for a polynomial where now I don't move the field k into a larger field L, but I slightly move the polynomial. So I put f lambda. And what is f lambda? It's a homogeneous polynomial of degree d, which is fixed, plus lambda times a polynomial of lower degree, which is also fixed, and the degree of g is at most d minus 1, and lambda is an element of QP, and this is homogeneous degree d. So you can look at the optimal exponent for the exponential sum for f lambda. And if you want, you can look at it in k or in qp or in L or the limit value of the optimal exponents. So let's put yeah. You can look at it in all these settings. And then the question is whether there is a semi-continuity in terms of the lambda. And you can compare the one of f lambda with f0, because that's easier. That's a homogeneous one. If lambda is 0, it's just fd. And here is a question, and also here is a question. So f0 should be the worst, f lambda should only be potentially better, and here is a question that it should also be better than n minus s over d, where n is a number of variables, d is the degree of of f0, and S is the dimension of the singular locus of fd, and this is only known for S equals 0. It's known by Iguza. But if you would know this kind of semi-continuity, then you can also continue and prove it for singular homogeneous parts. So it's a related question. Both these questions are related. One helps the other. So this is a different kind of semi-continuity that you can play at all these levels of a small field, large field, limit value, or all the p-adic fields for all primes together. So the sigma can have, voilà. And this is where I would like to stop for.
Are there questions for Raf?
Sorry, a stupid question. What's the relation between f lambda and f0? I mean, in the family? 0 is a generic point, or what is it?
f0 is just fd, because this is my parameter lambda. So if lambda equals 0, I just get fd, so it becomes homogeneous.
So it's right.
And I add a small, if lambda is very close to 0, this is a very p-adically small, very small
So that's what
thing
you
of
do.
lower degree.
Okay,
Yeah.
sorry. The number.
Any other questions?
So the two sigmas that you've mentioned. So the second one, I think, is just the f-low-canonical threshold.
Yeah.
Can you also relate the first one to some geometric thing? Or,
The Serre, with the Serre variant, the variant by Serre, it's the Serre variant of the low-canonical threshold, you could call it like that. It's intrinsic to an existential formula, so it's not so geometric, not purely geometric, it's given by an existential formula and some computations with it. So I don't know if it can be related to a geometric invariant that has been studied in other contexts, but this gives a whole bunch of new limit values sigma. For every existential formula you get a certain sigma, so some of them can be related to other invariants, some not.
Yeah, about this last question, when with Jan we introduced the motivic version, there were some computations of examples that were made by us and then by some other people, and it's very hard to get any geometric meaning of what these kind of things mean. I mean,
Yeah.
and I have a small remark. I mean, maybe the terminology Serre variant or Serre invariant is not so great because there is already something called Serre invariant.
Invariant,
So
yeah.
I don't know.
Yeah.
It's your choice, but
Yeah.
okay.
I call it the Serre variant of the Poincaré series.
Yeah, maybe you should. Maybe there's a way to slightly change the terminology to
Serre de
to
Nef.
less- to
Serre
less
de Nef.
confusing. Serre what?
Serre de Nef
Yeah. why not?
variant
Yes.
would be probably better.
Are there any other questions?
Yes, let me give one sentence with extra information. You can also play this game with the real field and the complex field. And then much more is known because you have a bunch of more techniques coming from differential algebra.
In this last question, on the one hand, you called it semi-continuity, but on the other hand, what's written seems to be a little bit stronger because you have inequality when? I mean, when lambda is in some neighborhood of 0? Or?
Yeah, let's say, I think always, but let's say lambda is close to 0. I think always, yeah. Should always hold. Yeah. Yeah, lambda is in ZP, say ZP, because otherwise the exponential sum needs tweaking. But okay. Yeah.
So let's thank Raf again.